Welcome to Electrical Lad, your trusted source for simplifying electrical, hydraulic, and pneumatic concepts in a clear and practical way. If you're new to this channel, don't forget to subscribe and tap the bell icon to stay updated on our latest videos. Have you ever looked at a ladder diagram and thought, what do all these symbols even mean? You're not alone. By popular demand, today we're breaking down the most common electrical symbols, like disconnects, relays, switches, timers, and sensors, and showing exactly how they're used in real control circuits, with clear examples. Every control circuit starts with safety, and that begins with the disconnect switch. This symbol represents a manually operated switch used to isolate power. Disconnects come in two main types, fused and non-fused. And in control panels, we typically use panel-mounted disconnects. Next, we have the control transformer. It steps down 480 volts to 120 volts AC to power the control circuit. Here, I'm showing the simplest symbol for a control transformer, but in practice, there are many variations. Some have multiple primary taps designed to work with other input voltages like 220 or 208 volts. We also ground the neutral side of the transformer to the control panel. This ensures that if there's ever a short from hot to the panel, the control fuse will blow, protecting the system. Next is the safety switch. This type of switch is commonly used for machine door interlocks and perimeter guarding doors. It ensures that motion is interrupted when a guard or access door is opened. Safety switches come in many different types, shapes, and sizes. Here, I'm showing two common versions, a key-actuated safety switch and a magnetic safety switch, both used to detect when a guard or door is properly closed. Now let's look at how these safety switches work in our ladder logic. You'll see that 4 switches are connected in series, and once all 4 are made, relay R1 energizes. R1 acts as a permissive relay, allowing control power to continue. But what exactly is a relay? Let's break that down next. This is the relay symbol, a key building block in control circuits. A relay consists of an armature, a coil, and contacts. When we apply power to the coil, it will generate a magnetic field and pull the armature down. Armature pushes the contacts together, and the contacts act like a closed switch. We can use the relay to power other devices or connect its contacts to a different circuit. For instance, we could hook it up to a solenoid valve. When it comes to relays, we need to understand normally open and normally closed contacts. Normally open means the contacts are open when the device isn't powered, and they close when it's turned on. Normally closed is the opposite. The contacts stay closed when the device isn't energized, and they open when device is activated. This applies to any kind of input or output device, like a proximity switch, a selector switch, or a relay itself. I will explain these devices a little later. Next, in line 3, we have 3 push buttons. PB1 is a normally open push button, while ES1 and ES2 are normally closed. Push buttons are usually momentary. They return to their original position when released. Normally closed push buttons like ES1 and ES2 are typically used as emergency stops or turn-off controls to quickly interrupt the circuit when needed. Push buttons come in a variety of sizes, like 16 mm, 22 mm, and 30 mm, depending on the panel layout and application. There are also several types of push buttons, including flush, extended head, and mushroom head styles. Mushroom head push buttons are commonly used for emergency stops, and some are maintained, meaning they stay in when pressed and only reset when someone pulls them out. Now let's take a look at how these push buttons are used in our ladder logic. Since ES1 and ES2 are normally closed, and relay R1 from our safety circuit is already energized, the R1-1 contact is closed. Now, when PB1 is pressed, it energizes MC1, the master control relay. As a result, the MC1-1 contact closes, creating a latching path around PB1. So even after PB1 is released, MC1 stays energized. Additionally, the MC1-2 contact closes and allows power to flow to the rest of the control circuit. At the same time, pilot light 1 turns on, clearly indicating that control power is active. Next, we'll cover selector switches and sensors. But before we dive in, we'd like to ask for a small favor. If you haven't already, please take a moment to subscribe to the channel. And while you're at it, don't forget to hit the notification bell so you never miss an update, and give this video a thumbs up if you find it helpful. Your support really helps us grow and keeps us motivated to bring you more valuable content. Our next rung introduces several new components: a selector switch, a limit switch, a proximity switch, and a solenoid. Let's first take a closer look at what each of these devices does, and then we'll break down how they work together in the ladder logic. First up is the selector switch. Selector switches typically come in three standard sizes: 16 mm, 22 mm, and 30 mm. They're usually available in 2-position or 3-position types, and they can be either maintained or spring-returned. You can also customize them with different contact blocks. For example, a 2-position switch might have one normally open and one normally closed contact, depending on how you need it to function in the circuit. Next in our rung are two switches: LS1, a limit switch, and LS2, a proximity switch. Let's start with LS1, the limit switch. Limit switches are mechanically actuated. When an object makes contact with the actuator arm or plunger, the internal contacts change state. They're commonly used for position detection, like sensing when a machine part reaches the end of its travel. Now LS2, the proximity switch. Unlike the limit switch, a proximity switch is non-contact. It detects the presence of metal objects using an electromagnetic field, making it ideal for environments where physical contact isn't reliable or could cause wear. In addition, proximity switches come in two main types: inductive, which detect metallic objects, and capacitive, which can detect both metallic and non-metallic materials like plastic, glass, or liquid, depending on the dielectric properties. Finally, in this rung, we have the solenoid symbol. Solenoids are commonly used to operate pneumatic and hydraulic valves, converting electrical signals into mechanical motion, either to shift a valve spool or open and close a fluid path. Now, let's look at how this rung works. Since the proximity switch LS2 is a normally closed switch, in manual mode, if LS1 makes and PB3 is pressed, the solenoid valve will energize. Another way the solenoid valve energizes is when the selector switch is turned to auto and limit switch LS1 is made. Now let's take a look at our next rung, which is the motor control circuit. We've already covered most of the symbols here, except for the timer contact and the motor starter. I'll explain the timer a bit later. For now, just know that it's normally closed. Let's focus on the motor starter. The symbol for a motor starter is the same as a relay, a coil. However, unlike a standard relay, a motor starter includes an overload element and a set of normally closed overload contacts. When an overload condition occurs, those contacts open, causing the coil to de-energize, which shuts down the motor and prevents damage. In addition, a motor starter includes auxiliary contacts that close when the main contacts close. Depending on the application, it may have one or several auxiliary contacts. Typically, one auxiliary contact is used to latch the control circuit, keeping the starter energized after the start button is released. We'll see exactly how that works as we go through this rung. Now let's go back and look at how the logic for this motor circuit works. Let's assume this motor is running a hydraulic pump. Now, when the start push button is pressed, and since the timer contact T-on-11 is normally closed, the motor starter energizes. Once it does, the M1-1 auxiliary contact closes, creating a latching path around the start push button, so the motor stays on. But what's the purpose of the timer contact T-on-11 in this circuit? We'll explain that next. But before we get to that, let's take a look at the 480-volt side of the motor starter. These are the starter contacts and overload protection on the 480-volt side. Once the starter coil is energized from the control circuit, the main contacts close, and the motor starts running. Also note, the symbol for a motor is a circle with the letter M inside. Now let's look at the symbols in rung 10, which energize timer 1, the same timer whose contact we used in the motor circuit earlier. First in this rung is M1-2, the auxiliary contact from the motor starter, which indicates the motor is running. Next is the pressure switch, a normally closed contact that opens when pressure reaches a set point. Then we have a flow switch, also normally closed, which opens when flow is detected. The flow switch is wired in parallel with the pressure switch. And at the end of the rung, we have the on-delay timer T-on-1, which is set for 1 minute. Also note, the symbol for a timer coil is a round circle, just like a relay or motor starter. Now let's look at how this circuit works. When the pump motor starts, it should produce both pressure and flow, causing the pressure and flow switches to open. However, if either switch stays closed, it means there's no pressure or no flow. In that case, after 1 minute, the on-delay timer T-on-1 will energize. When timer T-on-1 energizes, its normally closed contact T-on-1:1 opens, breaking the circuit and stopping the motor, since no pressure or flow was detected. Now let's look at the rung on line 12. This rung also uses the M1-2 auxiliary contact from the motor, connected to the normally closed level switch S15, and it's wired to an alarm and a pilot light. Now let's look at how this control circuit works. When the pump is on, if the oil level is at the correct height, the float switch opens and no alarm sounds. But if the level is too low, the float switch stays closed, triggering the pilot light and alarm to indicate a low oil level. Finally, let's look at our last rung. It starts with the M1-3 auxiliary contact, which tells us the motor is running. Then, there's a maintain selector switch to turn the heater unit on or off, followed by a temperature switch. The last device is a contactor coil that controls the heater. Now let's see how this rung works. When the pump motor is running and the selector switch is set to heater on, the normally closed temperature switch allows the heater contactor to energize, closing its contacts and powering the three-phase heater. Once the preset temperature is reached, the temperature switch opens, turning off the heater. As long as the selector switch stays on, this process operates automatically. Keep in mind, temperature switches have hysteresis. They shut off at a high set point but don't turn back on until the temperature falls below a lower limit. So let's recap. We started with the disconnect, transformer, and safety switches. Then we added push buttons, selector switches, and sensors. We saw how relays, timers, and motor starters interact to run and protect a hydraulic pump, trigger alarms, and control a heater automatically. All of it tied together through real-world ladder logic. If this breakdown helped you understand ladder diagrams better, don't forget to subscribe to Electrical Lad, hit the notification bell, and give us a thumbs up. Got a circuit you'd like us to explain next? Drop it in the comments. Until next time, stay safe, stay curious, and keep learning.